Hello everyone, this is going to be the 1.6 practice problem solutions. So I'll just go through everything and then I'll explain it after. Okay, so for the first ones we use limit laws, and just as a reminder, it's these ones. They're not, I don't think you would get confused on these. You just split each term up and then factoring out constants and then just substituting what your x value is approaching to. For these ones, these are direct substitutions, so you just plug in the number. But for this one, you have to do a little bit of factoring. So t squared minus 2t minus 8 becomes t minus 4 times t plus 2, and then you could cancel out the t minus 4, and then you get the limit as t approaches 2 of t plus 2, which equals 4. Then this is a direct substitution again, number 4, because when you plug in negative 2 into the bottom, it's not 0, so everything's okay. This one, instead of having to do all the algebra when you're substituting it in, just recognize that the top is, when you factor it out, you get x minus 3 times x plus 2, and then since 3 is a 0 of that top function, the whole thing is going to be 0. For number 6, you have to recognize your a cubed minus b cubed formula. So just as another reminder, that's a cubed minus b cubed is equal to a minus b times a squared plus ab squared, or plus ab plus b squared. And then for the bottom, it's a squared minus b squared equals a minus b times a plus b. T minus 3 gets canceled out, and then you're left with the limit as t approaches 3 of t squared plus 3t plus 9 divided by t plus 3. And then after simplifying down, you get 9 over 2. As you get to more algebraic questions where you have to do a lot more algebra, I usually just do my work under the problem, so then I just write one limit because I'm a lazy person. So in this problem, you FOIL everything out, which means, or you get h squared minus 6h plus 9 minus 9 divided by h, and that becomes h minus 6. And then you take your limit, and then you get negative 6. This one, you multiply it by conjugate. I did my work under again, and then I wrote one limit. The trick for these is recognize that a minus b times a plus b is equal to a squared minus b squared. So in context of number 8, it would be square root of 9 plus h minus 3 times 9 plus h plus 3. That's going to be square root of 9 plus h squared minus 3 squared. 9 minus 9 plus h, you get h. And then since there's an h down here, that h cancels out with the top h, which leaves you with this. For number 9, you have to recognize that this function right here has an asymptote at 3, which means this is an asymptotic limit, which means the limit does not exist. Now this one, there's a good amount of algebra, so I did it under again, and using using a squared minus b squared, that formula, you get this, and after simplifying you get this, and then it's just a direct substitution. for these one side limits, I did it like this to show like how it works using the piecewise, but in reality, you can just plug it in. When you plug it in, you get 0 times x minus 2, which gives you minus 2. But if you were to do it like this, you see where x plus 4 equals 0, which is negative 4. So that would be your value, your value right here. And then for here, you keep it positive. For here, you multiply it by a negative. What the heck? Which is why it becomes negative x minus 4. And then you take the limit of the right and the left, and you get negative 2 on both sides. For this one, for this one, it's the same thing. Where does this equal 0? At 0. So then your right side is going to be greater than 0, and your left side is going to be less than 0. And then you keep it positive, which means it's still going to be a minus. You make it minus, which means it's going to be a positive since you're subtracting. And then you take the limit of both sides. This is equal to 1. This is equal to 4 over 0, which is undefined, which means it does not exist. For this one, it's the same thing. Where is this equal 0? I wonder. Oops. At 0. So then this is going to be when x is greater than 0, x is less than. So this is going to be your right and left. You keep it the same. You make it negative. You get 0. And then 2 over x. You find the limit from the left side. And then you see that they're not the same. So it does not exist. Now my favorite, squeeze theorem stuff. So just to recap what these symbols mean, these ancient Egyptian symbols. This means for all x, what else is there? This means it's an element of that set, and in this case your set is the real plane, so then the real plane, which is all real numbers, so no imaginaries. And then this one, the little arrow, means implies that. Okay, now if you remember our conditions for the squeeze theorem, first we need our inequality where I think it was f g h. You need this inequality to be true, where g of x is equal to whatever your limit is. And then the next condition is that the limit as x approaches a of f of x equals the limit as x approaches a of h of t, or h of x. H of x. So the first thing I wrote, just to help like beginners, I guess, is to write your inequality down first before you write your statement. So cosine is between -1 and 1, no matter what your inside of the cosine is. So if you change it to 1 over x, it will be the same. Then if you multiply everything by x squared, you get this inequality, which is your first condition. And then I wrote, since cosine is between -1 and 1 for all x in the real range, it implies that since -1 is less than cosine x, which is less than 1, for all x in the real range, it implies that negative 1 is less than cosine of 1 over x, which is less than 1. Multiply each term by x squared to get negative x squared is less than x squared cosine of 1 over x, which is less than x squared. And then if you take the limit of your outside functions, they're equal, which is equal to 0. And then you could state your theorem, which is squeeze theorem. So by squeeze theorem, since x squared cosine of 1 over x is between negative x squared and x for all x, and the limit as x approaches 0 of negative x squared and x squared are equal, it follows that the limit as x approaches 0 of x squared sine of 1 over x is equal to 0. And then I'll go to this one first. It's basically the same thing here. It's literally the same format. You just say since the range of whatever for all x, and then you say what you do to the inside, which is this and that, to make it look like this. And then you just take the limit of the outside, and then you say by squeeze theorem. And then you state like your conditions. Like, okay. Now this one, if you look at this one and you do your inequality, you get 1 divided by 3 minus x is less than 2 minus sine of 1 over x divided by 3 minus x is less than 3 divided by 3 minus x. So if you notice, if you take the limit as x approaches 0, you get 1/3 from this one, and then you get 1 and the other. So this is a case where the second condition is not true, because the limit is not the same, which is shown here. If that's the case, you can just say, therefore, squeeze theorem cannot be applied. But the limit to this actually does not exist. Not because of this. This does not guarantee that the limit does not exist. It's just a special case. So as x approaches 0, your bottom is basically 2 minus sine of 1 over x divided by 3. And if you remember, sine of 1 over x is between negative 1 and 1. So what you could do is you could just plug each of these values in for sine of 1 over x to see where your range will be for your answer. I don't know why I draw 2 dots, but yeah. So when you plug in negative 1, you get 2 over 3, which is your minimum value. And when you plug in 1, you get 1. So that means at 0, if you have a plane here, and this is 2/3 and this is 1, as it approaches 0, it's just bouncing back and forth between 3 and 1. So it looks like a really fast wave. And that's why it does not exist, because it's just oscillating between those 2 points without actually ever reaching a single point. So now just to do a little breakdown of squeeze theorem, there's two steps. There's your conditions, and then state your conditions. So our conditions is that you have the inequality, which is f of x is less than or equal to g of x, which is less than or equal to h of x. Usually that one always happens. But then your limit one, which says your limit as x approaches of f of x must equal the limit as x approaches a of h of x. And you can see in number 1 and 3, I do those. So our condition 1 will be yellow, and our condition 2 would be green. So in the first one, our condition 1 is right here. And our second condition is right here. And the third one, our first condition is here, and our second is right after. Now for the state condition part, you just state it. You state your first condition, which is the inequality, and then your second one, which is your limit. Again, it will be in yellow and green. So just the first thing I said, and then wait. Oh, I forgot it here. Uh-oh. This one should say the limit as x approaches 0 of square root of x equals the limit as x approaches 0 of 2 square root x. So let's redo that. This is our yellow. This is our green. And in the top one, this is your, where is it? This is your yellow. This is your green. And that's all. This will be like the first of many writing portions you do in Calc 2. In 1.7, there's a lot of writing, so get ready. That's all. Bye bye.